All right, in this video I'm going to be working the problems from BC Review number 7, which is free response that covers parametric equations, function analysis, and also some of those table data with context problems. So I'm going to start off, and I'm going to start with 2016 BC number 2. And so I'm going to need to bring that in, probably zoom out a little bit. Yes. All right. So here they're giving us an equation for dx dt and the graph of y of t. Okay, so they're giving us the x velocity but the y position. And that's, I think, the subtlety of this question, is the fact that one of them is the derivative, one of them is the original, one of them is given to you in an equation, one of them is given to you as a graph. There's all sorts of stuff. It's like a mixed media situation. So, find the position of the particle at time t equals 3. Okay, we're going to be able to do that. We're going to say that, let's scoot that up, yeah. So, the position of the particle at time t equals 3 is going to be, well, let's just start with y of 3. That's going to be a little bit easier. How about y of 3 equals negative 1/2? And you can see that it went from negative 1 to 0. Oh, you can. You can see it went from negative 1 to 0 as x increased by 2. So that is, increasing by 1/2 each time I run over by 1. So that is negative 1/2 for sure. Okay, x of 3 is going to be equal to x of 0 plus the integral from 0 to 3 of x prime of t dt. Okay. So that's going to be equal to x of 0 was 5 plus the integral from 0 to 3 of t squared plus sine of 3t squared dt. Okay, because of this is an integral you have to run on the calculator. There is no closed form antiderivative for this thing. Hold on just a second. Oftentimes I'm going to skip the showing you how to run this through the integral just to keep this video a little bit shorter. So yeah, I'm going to just go grab the answer real quick. And that's 14.377. Okay. So the position at time t equals 3, I'll just clearly state my answer. Position is x is 14.377, y is negative 1/2. Let's see, what's the second part? Find the slope of the line tangent to the path of the particle at t equals 3. Okay, that's another one we're going to be able to deal with. Okay, for part B, we know that dy dx at the point where t equals 3 is going to be y prime of 3 divided by x prime of 3.
Hey, Mr. Hub?
Hold on just a second.
Yeah.
All right, now y prime of 3 is going to be the slope of this graph at t equals 3. That's looking like positive 1/2. And then dx dt at t equals 3, I'm just going to plug in 3 here. So that would be 9 plus sine of 27. Okay, this is a safe place to stop, right? Especially, like, I don't know, say something really bad happened and you didn't have your calculator. You can stop here and get full credit. I am going to just show you that this is actually equal to 0.050. Okay, and then for part C, what is part C? Find the speed of the particle at time t equals 3. Well, it looks like I will be able to fit all of this onto this one sheet here. For C, because speed is equal to the square root of, well, in this case, x prime of 3 squared. This is t equals 3, right? Yes. X prime of 3 squared plus y prime of 3 squared, which is going to be equal to the square root of 1/2 squared plus this number squared. So again, if you had no calculator, we could stop here and we could be happy, but I know you all generally like to get to a 3 decimal solution. So that was 9.969. D, total distance traveled. That's where we're going to integrate speed. Okay? Distance on 0 to 2 is going to be equal to the integral from 0 to 2 of dx dt squared plus dy dt squared with respect to t. But the thing is like, I don't have a formula for y prime. If we go over here and we look, y prime is -2, and then it's 0, and then it's a half. So what we're going to have to do, since we're only integrating from 0 to 2, I'm going to split this up into two different cases. One where y prime is -2, and one where y prime is 0. So I'll come back over here, and I'll do that. And this is going to be the integral from 0 to 1 of the square root of x prime of t squared. Now, we don't have to copy, what is it, t squared plus sine of t3 squared. We don't have to copy that. They know if you say x prime of t, you mean dx dt. Plus, well, that was -2 was dy dt. We're going to square that. And then we'll add that, I guess, dt, plus the integral from 1 to 2 of x prime of t squared plus 0 squared dt. And then, you add these together, you run it through the calculator, and that's going to be 4.350. And that's the first parametric equations question. This one was very direct and straightforward, and I liked it. And, we should all be so lucky as to get a problem like this on our AP exam. But that's not always the case, right? Sometimes the questions they ask are less direct. So that's why I pulled in 2015 BC number 2. Very similar questions, right? This one, I mean, it's different in the sense that they gave you, what is it? They gave you dx dt and dy dt as an equation, more or less, algebraically. But they're going to ask you the backwards question. They're not going to ask you what is the speed of the article, or what is the speed of the particle at time t equals 3. They're going to say, find me the time t that makes the speed 3. So it's kind of a backwards line of questioning. But overall, it's the same thing. But it is the type of thing that we'll need to use our calculator to solve an equation. And that's one of the things that we're required to do in this class, so it's probably good that we practice. Find the x-coordinate of the position at time t equals 2. This is going to be very similar to what we did in the last problem with the first part. So I'm going to say that x of 2 equals x of 1 plus the integral from 1 to 2 of x prime of t dt. Now, I'm just saying on a safety level, right? Like, I know you know that that's dx dt. But nowhere did they ever, define that. I think that that's a calculus knowledge piece to know that the derivative of the position vector is the velocity vector. So just to be safe, I'm going to call that cosine of t squared. And so that's going to be equal to, pardon me, just going to grab a calculator. I don't think I've run this integral yet. I don't have these decimal answers. Oh, that's an answer to a later one. Oh, no. Oh, no. Oh, maybe. Who knows? Looks like I've been doing this problem. Cosine of t squared, e to the 0.5t. Clear that out right now. And I want x of 1 is 5. Well, maybe I'll just run math 9 from, 1 to 2 of dx dt. I put in y1 dt. I got negative 0.443 equals 5 plus negative 0.443. And that's a decent position, right? All right. For 0 to 1, there is a point on the curve which the line tangent to the curve has a slope of 2. At what time is the object at that point? Okay, slope of the tangent line, that's dy dx. So that means that y t divided by x prime of t is equal to 2. And again, because nobody ever actually defined x prime of t and y prime of t, I'm just going to really be explicit. Show the reader that I do know what I'm talking about. Divided by cosine of t squared equals 2. Now, this is the equation that I want to solve for t. So I'm going to just run it through the calculator, and I'm going to report my solution right here. Right, so I'm going to go over here, and I want, well, dy dx is dy dt divided by dx dt. So I'm going to make a fraction bar, y2 divided by y1. And if I want this thing to equal 2, oh, I didn't notice there's horrible glare right there. But here, there's stripes. Who knows? I don't know what's going on here. If I subtract 2, that would equal 0, right? If that fraction equaled 2. So I'm going to graph this on, I don't know, it said t is greater than or equal to 0, so I think 0 to 5 should be appropriate. I'm going to graph it on 0 to 5 and hope for the best. Okay, there I've got one place, but it's like it only said one place, and it's like, okay, all right, that's reassuring. And it's, oh, okay, it came close, but okay, I'm feeling better about this now, and we just got to let it graph, you know. There is a setting you can put your calculator in to have it graph faster, but the one I have doesn't seem to have that setting in the menu. All right, so I'm going to calculate a 0. 0 is left bound, 1 is a right bound, 1 is a good guess. 0.840. Okay. So one of the things, you know, calculator-wise, if you're going to use the calculator to solve an equation, we need to report what equation we used it to solve. Okay. We don't want to just come up with a t-value out of nowhere. I had something else to say about this. Oh, okay. Notice how it only graphed black, right? Y3. That's because I turned off the graphing for Y1 and Y2. If you wanted it to say not graph Y3, I don't know why you would want that, but you highlight it. You see how like you highlight the equal sign, you press enter, it makes it not, you know, dark anymore, and that means it's not going to graph. Okay. For part C, we want to find out when is the speed equal to 3. Well, speed equals 3. Okay, so that's the square root of x prime of t squared. That equals 3. Okay. You know, if you wanted to call this, what, cosine squared of t squared plus e to the 0.5 t squared would be e to the t equals 3. I mean, I'm going to do it to be safe because I'm sitting here at 12 minutes, 30 seconds, and each of these you have 15 minutes for on average. So, like, I'm doing fine on time. Okay, and so what I want to do is I want to take the square root of, okay, no glare, dx dt squared plus dy dt squared. I want it to equal 3, so I'm going to subtract 3 and see where it equals 0. Okay, I'm going to graph it on the same window because I feel like that should be fine, right? And it's happening. Okay, it's between 2 and 3. Looks like that's going to be all for that. Yep. All right, well, let's calculate a 0, 2 to 3, 2.196. And then part D, I think, no, that's a different problem. Total distance, no, this is very, very predictable. The integral from 0 to what? To 1. Of the square root of dx dt squared plus dy dt squared, maybe I'll just call that cosine squared of t squared plus e to the t, right? You're just integrating the speed function. And then I go over here, and I know what I'm going to do. I've already got in Y3, I've got most of this written, or typed, I guess. So rather than this all again, I'm going to just say, all right, Y3 is the speed now. So I want to integrate from 0 to 1 speed with respect to t, and I get 1.595. Can't see that, but I wrote down 1.595. That one, see, like, as far as what they were asking, it was basically the same, but you had to do a little bit more activity to find those answers. And who knows, maybe the first question in 2015 was really easy, and the first question in 2016 was really hard. And so it always ends up balancing out. You don't have to worry. So, let's see, what comes after that? Oh, it's the function analysis question, so I need to just go kind of browse through these. I found it. The first one is the one that's got the kind of curved graph with the areas. Okay, cool.
Yeah.
Wonderful. This one's from 2013. This is a good old-fashioned AP calculus question. And honestly, I'm just going to continue to hit you with these function analysis questions because, you know, a few things in life are guaranteed. And this is not guaranteed. I just was looking at 1 year of Cal BC free response that didn't have this type of question on it. They must have been hammering them with it in the multiple choice. Because it's nearly guaranteed that you're going to see one of these. So, the figure above shows the graph of f prime, which is the derivative of f. F prime is horizontal tangent lines at 1, 3, and 5, although I don't know that that's actually going to... Oh, yeah, for concave down, I guess that's going to matter. And the areas of the regions are labeled in the figure. And f is defined for all real numbers. Okay, that's cool. Find all values of x on the open interval 0 to 8 for which the function f has a local minimum. Okay, justify my answer. I can do that. Okay, so f has a local minimum anytime its derivative goes from negative to positive. F prime goes negative to positive. Okay, that's what I'm looking for. Hey, look, there it happened. That's at x equals 6. So x equals 6 is what I would do, I would just probably write this sentence that I'm just going to kind of like mark in orange. I would just say this and leave it at that. X equals 6 is a relative minimum because f prime of x goes from negative to positive. And me personally, just to be safe, I'm going to write out the words. I'm not going to write it like that, right? I'm definitely not going to write dash to plus, right? They might not understand that. Determine the absolute minimum value of f on the closed interval 0 to 8 and justify my answer. Okay, I'll do that. The absolute minimum, that's on a closed interval. I'm going to need to run the candidates test, right? So I've got x values and f of x values, and I'm going to just choose the lowest value of f of x out of this table. Now, we've got the endpoints. We definitely need to consider the endpoints, x equals 0, x equals 8. But we also need to consider the critical points, and that would be where f prime of x is equal to 0. Go back here to the graph of f prime. That's x equals 1, x equals 4, and x equals 6.
Because it's asking for an absolute minimum, can you just use the relative?
Yeah, yes. Okay, question was, because it's asking for an absolute minimum, are you good to ignore 1 and 4, or 1 and 4, yeah, and only use 6? And that is true. The absolute minimum of function will either happen at an endpoint or at a relative minimum. I'm going to do all of these points just be easy. If there had been more to computing these f values than just like, you know, all these areas are integers and it's really nice, and I'm actually, since it starts at 8, I want to backtrack all the way, and I mean, I think you and I both know where the absolute minimum is occurring, so it just helps for me to use all of them. But yes, I want to unequivocally state that if you are looking for, say, an absolute maximum, and you've got 2 relative minima and 1 relative maximum as all the critical points in your interval, all you have to consider is the endpoints and the relative maximum. Because how are you going to have an absolute maximum at a relative minimum? Doesn't sound very likely to me. So I've got 1, I've got 4, and I've got 6. Okay. They told me that f of 8 was something. F of 8 was equal to 4. So right down here at the bottom. So f of 8 is equal to 4. Now that means just backtracking that f of 6 has to be negative 3, right? Because if I added negative 3 and I added 7, I'd have 4. So I've got negative 3 here. And then backtracking again, now this is a little tricky, right? Back to here, I would probably need to have 0. Because then when I subtract 3 for it being underneath the x-axis, I need to get to negative 3. Then I'm going to probably subtract 6, going backwards back to 1. Okay, so I'm thinking negative 6, but I definitely am going to think about this. If f of 1 was negative 6, Then I would add 6 to get 0. Then I would subtract 3 to get -3, and I would add 7 to get 4. I feel good about this. Okay, and then the last one, I'm going to subtract 2 more, and so I'll have -8 at x equals 0. Let's see, like, does this seem reasonable? Could I start at -8, add 2, that's -6, add 6, that's 0, subtract 3, -3 plus 7 is f of 8 equals 4. I feel good about this. Now, I've found it. Here it is. That's the minimum value. Okay, so the absolute minimum value for x being in the closed interval 0 to 8 is f of 0 equals -8. Okay. Part C is, where is the graph of f both concave down and increasing? Now, I'm going to kind of preemptively explain my reasoning here. And I'm also going to not distract you with the work I've done in a different part. I'm going to flip this thing over real quick. All right, so concave down and increasing. Okay, so for part C, concave down is, if we're looking at the graph of f prime is decreasing. And what f, so I should probably say f, increasing tells me that I need to be looking for f prime positive. Okay, so where is this graph positive and decreasing? Here's a place, there's a place. I feel like after 8 there would be another place, but you don't know that. It might be about to turn and go up. You don't know. You have no idea what's going to happen. So I'm going to say, well, I said it. Okay, 0 to 1 and 3 to 4. Okay, I wouldn't personally recommend giving them one interval and one inequality, but I just want to make, again, really emphasize that in AP Calculus, we do not care about interval notation versus inequality notation, and we don't really concern ourselves with the endpoints either. So you could say, you could make these square, you could make these not, or you could make these strict inequalities, and nobody cares. So analysis level discussion depends on the definitions you take early in the course. Nobody's going to penalize you for when they think another. All right, then G. I kind of liked this one. I thought this one was nice, and I almost got tricked by it when I was working it in first period this morning. Okay, so if G is f of x cubed, right, so G of x equals f of x taken to the third power. We want the slope of the tangent line. Well, we know the slope of the tangent line. That means the derivative. So I'm going to say g prime of x. I'm going to take the derivative starting with the outside. 3, reduce the power by 1, keep the inside the same, and then multiply by the derivative of the inside. So that g prime of 3 is equal to 3 times f of 3 squared. Well, f of 3, they just helpfully told me, is -5/2. And then f prime of x. Man, this is, hopefully you did not get tricked by this the same way I did. F prime of 3, I was like, oh, it's going to be 0. I was like, wait a second, why would they say it was 0? Because you could be right for the wrong reason. And then I realized this is the graph of f prime, and f prime of 3 is going to be equal to 4. So we're just going to call it that times 4, and we're going to be happy, and we're going to move on. Okay, the next one is not a real AP Calculus question. Like, the graph is real, and I think the first part of the question is real, like it was somebody's. But a lot of these, they can get a little repetitive. So what I did was I asked you questions, like kind of different questions from different years. So g of 3, that'll just start with the direct part. G of 3 equals the integral from -3 to 3 of f of t dt. Okay. from -3 to 3, this is -3, not here. Okay, that was another mistake I've made in the past. So I'm going to say that it's equal to the sum of this whole triangle and then this small triangle here. So that's 1/2 times the base is 2, 3, 4, 5. The height is 4 plus 1/2. The base is 1 to go out to 3, and the height is -2. Okay, and then that's going to be an exact answer. I don't need to simplify. This is not calculator. It'd just be a waste of time to simplify. Right? All right, I found g of 3. But the question is, does the graph of g have a point of inflection at x equals -3 and justify my answer? Amongst the in-person people, what are we thinking? Yes or no?
I put yes.
Okay.
I put yes and I switched my answer.
Okay.
Wait, what is the answer?
The answer is yes. Okay. So you may be like the people in my class in 2016. This is like a question that's taken from 2016 BC number 3. What happened? I actually don't remember if it was number 3, but I remember it was the function analysis question that looks like mountain peaks. I remember them all coming out of the exam at my old school and being like, hey, is that a point of inflection if you're looking at the graph for the derivative? And I was like, oh, yeah, it definitely is. And I never told them that. And but that was my first year teaching Cal BC. And since then, I have emphasized it on a yearly basis. But this year, what did I emphasize? What did you hear? Who knows? Does the graph of g have a point of inflection? Well, the graph of g will have a point of inflection anytime g double prime changes signs. Okay. Well, g prime of x, I haven't mentioned this yet. I haven't needed it yet. I know that g prime is equal to f, so I'm going to clearly write that here. And since we're going to talk about the inflection points of g, I might as well talk about the fact that g double prime of x equals f prime of x. Okay, at x equals -3, f changes from decreasing to increasing. Indicating that f prime, which is equal to g double prime, has changed signs. From negative to positive. This is probably more specific than you need to write, but I just want to explain my reasoning, you know what I'm saying? So change sign from negative to positive, thereby indicating a point of inflection on the graph of g. Yeah, so but
Is it ask if that how does one of that equals -3? Would it be no?
I would say no, because over here the sign of the second derivative is 0, and over here the sign of the second derivative is also 0.
Yeah.
So yeah, but had it gone, had it looked like this, then I would say yes. Yeah. Because the second derivative not existing does not preclude you from having a point of inflection, which is an inflection point on G. Okay, that's cool. That was way more specific than you need to be.
Just to confirm, because I was saying the derivative didn't exist because it was sharp.
Oh yeah. That is not untrue. Okay, so I don't know if you got picked up, but she was saying that the second derivative of G failed to exist at x equals -3, and that is definitely true, right? That the limit of the difference quotient doesn't exist there, but the idea with a point of inflection is that the concavity changed sign, or the concavity changed there. And over here, f is decreasing. And since f is the derivative of g, that basically means f prime negative means g double prime negative means g is concave down here. But after this point, g is concave up because f is increasing.
Okay.
So and we went from concave down to concave up. That is a change in concavity. That is a point of inflection.
And even if it can be either 0 or not existing.
Yes. Yeah, and the second derivative, it could be 0, but in this one, what we're really seeing is a jump discontinuity across the x-axis. You know, the second derivative went from positive to negative. Specifically, I mean, by the slopes of those lines is kind of the negative and positive numbers. But I'm going to move on. For part C, this one, there's two different ways you could do it. You can just cook yourself up an antiderivative, which maybe I'll do it both ways. I'll do it first the way that I would think to do it, which would be to use my integral properties. Okay, I'm going to say that this is equal to 2 times the integral from -5 to 4 of f prime, because that is going to be really easy, plus the integral from -5 to 4 of 4 dx. This one is from 2019. I didn't use I really like the graph that they use on 2019 because it's got a semicircle that's upside down that sits above the x-axis, making the geometry computations much more difficult than usual. But it was only really integral questions, and I still wanted to get that good point of inflection, increasing and concave down, all that good stuff. I wanted to get that in there. I will bring that 2019 function analysis problem to you eventually. Okay, anyway, so this is equal to 2 times, well, I take an antiderivative, that's f, I plug in 4, I plug in -5, that's the integral. And this thing, well, this is a rectangle. If that's 4, then I can go up to 4 and back to -5. And I can see that this is a rectangle with width 9 and height 4, so it's going to be 36. Okay? Yes, you could take an antiderivative and have 4x, and you'd have 16 minus -20, and you would get 36. But, you know, I like this better. So I need to actually figure out what f of 4 and f of -5 are. So that's -4 and 2. And I'm going to just leave it like that. 1 and 2, I'll work this in pink off to the side. We could say antiderivative would be 2f of x plus 4x as x runs from -5 to 4, which is 2f of 4. f of 4 was -4 plus 4 times 4 minus 2 times f of -5 was positive 2. That's tricky. Plus 4 times -5. And you could just stop there. It's the same number. Just more opportunities for errors, in my opinion. Okay, part D. This one is integration by parts. And you know that because you're seeing multiplication in the integrand and nothing is the derivative of something else, also in the integrand. Okay. I think because the text is small, I might zoom in a little bit. And so, and also, this is one of the main ways I tested you on integration by parts. Thought I had something else to say about this. Oh yeah, this is one of those things that, you know, I've been giving this problem out for years, but I only really started focusing on it last year for the digital exam because I was like, oh, this one's calculator proof, internet proof, with a table or with a graph. And I used it this year extensively, but this one's here to stay. Like, I really think. I think this is a really good way to ask about integration by parts. So I would not be surprised for you to see this either on your multiple choice or on your free response. Wouldn't surprise me in the least. This one I made up, though. Anyway, I'm going to let u equal something that's nice to take the derivative of. Both of these are pretty easy to take the derivative of, but if I take the derivative of f double prime, that's f triple prime, and I don't really know the first thing about f triple prime. I don't really even know much about f double prime looking at the graph. Besides, you know, I could probably figure it out in a piecewise sense because f is piecewise linear. Wait a minute. F double prime. Wait, shouldn't this be 0? Hold on, I'm going to pause this real quick. All right, this is going to require more thought, but like just looking at f of x, looking at the graph of f, talking about f double prime, f is piecewise linear, meaning f double prime should be constantly 0 anywhere where it's well defined. Also, I should have, it would be okay to integrate over this thing, because I'm going to have at worst just like jump discontinuities in the second derivative. but it's just going to be 0 with holes, I think. So I feel like I should constantly be integrating 0 right here, but I'm just going to carry it through as if I wasn't, and maybe it'll just make more sense when I actually do this. Okay, we'll see. Okay, let's look at, well, you know, I know, and I know somewhere in there y'all know, but you need to write it down more times, that the integral of v is equal to u times v minus the integral of v du. And if this is an integral from -4 to 3, then we're going to have to evaluate this from -4 to 3, and we're going to have to run this integral from -4 to 3. Okay. So this is going to equal x f prime of x from x running from -4 to 3 minus the integral from -4 to 3 of v du. That's f prime of x dx. Okay, which is 3 times f prime of 3. Okay, if we go back up to the graph, f prime of 3 is this -2 right here, that slope. F prime of -4 is going to be -1 also. So I'm just going to, that is a slope of -2, right? Yeah. Okay. Feel good about that. Okay, so that's 3 times -3 minus -4 times -1 minus. Okay, this integral is the difference in f from -4 to 3. So at x equals -4, the height of the function is 1. Even though it doesn't really look like it. And at x equals and x equals +3, it's looking like -2. Let's see here. This is -9 plus 4 -2. Okay, I'll be honest. I don't know what's going on here. I feel like I may have, violated one of the conditions to integrate this thing at all. Or maybe there's just something I'm not thinking of. But this is the set of steps you would take to solve this integral, provided all of that data.
Yeah.
I have to think about that. Why this is not coming back 0? I feel like it should be, because prime is constantly 0. Anyway, not a huge deal. We will. Somebody's going to figure it out and report back to me, I'm sure. And if not, I know a couple people I can maybe ask. Poor students in my multivariable calculus class. I'm going to get hit with that tomorrow, unsuspectingly. All right, and then find the limit. This one's really nice because I've got, 2 to the x is 2 to the 1 minus f prime of 1 is -2. Half of f is +2 at x equals 1. And arctangent of 1 is pi over 4, which, yes, you need to know that. And this is not 0 over 0. Okay, it's not anything over 0. This is a number. So that's the limit. Okay, don't forget that can occasionally happen. Don't just start it off by presuming you need to take the derivative of the top and the bottom.
If you leave it as arctan 1 on the bottom, is that okay?
All right, so the question was, do I really, really have to evaluate arctangent of 1? And it's sometimes yes, sometimes no. And since it's sometimes yes, sometimes no, it's best that we know. Because there's only 3 values of arctangent that you need to know. That's arctangent of 0 is 0, arctangent of 1 is pi over 4, and the limit of arctangent as, the tangent goes towards infinity, and that's pi over 2. And of course the negatives of those would also be something they would ask you about occasionally. All right, so that was it for that one. I'm going to need to speed up my roll here because I can see I have a limited amount of time left in my day. But hey, which one came first in the table? The tea, yeah, the tea and biscuits, of course, yeah. All right. So as a pot of tea cools, the temperature is H, where T is measured in minutes, is H is measured in degrees Celsius. All right. Okay. Oh, I had a few points to make about this set of problems. All right, first of all, part A on all three of these is just the rise over run thing. Don't forget about that, right? Don't forget that if we want to approximate the rate of change of the temperature of the T, which is H, I'm going to do rise over run. It's going to be approximately equal to the slope between these 2 points, because 3.5 sits in there. So that's 52 minus 60. Oops, that's not what that is. 52 minus 60 divided by 5 minus 2. And then use the data. Okay, if I had to show units of measurement, I would say degrees Celsius per minute. Right? Degrees of this divided by degrees of that.
Question?
Yes.
If you just say degrees, is that wrong?
Yes. Yeah, because it's the rate of change of the degrees.
Sorry. I mean, if you just say
degrees per minute.
Like I never specified Celsius.
No idea. It sounds unsafe to me,
Okay.
but it's going to have to do with like the kind of like the law for that question that we don't have access to.
So you should always say.
Yes, definitely. I said whatever this says. I generally say unless there's an abbreviation like the degree symbol for degrees. All right. Using correct units, explain the meaning of 1/10 of the integral from 0 to 10. Oh, that's a good one. We can do that. Is the average value of h. But I'm not going to say h, because they said in the context of this problem, right? Saying that is the average of h on 0 to 10 is interpreting it on a calculus level, but not in a worldly level. So what does h mean? The temperature of the T. So I'm going to write that in exactly as they wrote it. And using correct units, and what would the average temperature be? It would be in degrees Celsius. For 0 to 10 hours. Thank you. Yeah, you don't need to let T cool for hours. Thank you. That's helpful. All right. Use a trapezoidal sum with the 4 sub indicated by the data in the table to estimate this. Okay, we can do that. We've got this. So what we're going to do is we're going to say 1/10 of the integral from 0 to 10 of h dt is going to be approximately equal to 1/10 of, and okay, average the bases, multiply by the height, right? So I'm going to average the 66 and the 60, multiply by the, well, it's width here, plus average 60 and 52, multiply by the width, that one's 3. Average 52 and 44, multiply by that width is 4, and then average 44 and 43, and multiply by the width is 1. All right, and it's really important that we write it out like this and not like draw a bar graph or draw all the trapezoids, because we need to see that addition and multiplication to get the Riemann sum credit. And it's not Riemann sum, it's trapezoidal sum, but to get that credit. Okay. Evaluate the integral from 0 to 10 of h prime and tell me what that means. This is one where we can actually let our work dictate what is going to happen here. Integral from 0 to 10 of h prime of t dt, I'm going to find an antiderivative of it. And I'm going to say that, oh, that's h of 10 minus h of 0. H is the temperature of the T. Oh, that makes sense, right? Because the integral of the rate is the net change in the total. Okay, so represents, oh, I should probably actually find that value, right? H of 10 minus h of 0 is 43 minus 66. And I'll say degrees Celsius. The change, I might say net change, but you don't need to, in degrees Celsius of the temperature of the T. what's part D? Oh, okay. This one I'm probably going to need a new sheet before. At time t equals 0, biscuits with temperature 100 degrees Celsius were removed from an oven. The temperature of the biscuits at time t is modeled by the differentiable function b, for which it's known that b prime is that. Using the given models at time t equals 10, how much cooler are the biscuits than t? Well, I just need to find b of 10 and compare it to h of 10, which is equal to 43, and then subtract them. B of 10 is going to equal b of 0, which is 100, plus the integral from 0 to 10 of b prime of t dt. Okay, so I'm going to say 100, set this down, plus the integral from 0 to 10 of negative 1384 e to the negative 0.173 t dt, 34.183. Yeah, I'm still visible. And the biscuits are that much cooler, okay? If you'd been thinking ahead, maybe you could have, like, I don't know, used the calculator to find that ahead of time, but now that once I've got the number, it's not worth more typing. All right, now, okay, I'm not moving fast enough. So, use the data in the table to find an approximation for h prime. So that will be 18.5 minus 15.5 divided by 7 minus 5 inches. Oh, this is the wrong problem, but it's okay. Per minutes. Show the computations that lead to my answer. All right. Approximate the value of the integral from 0 to 10 of h of t dt using a right Riemann sum with 4. Okay. So I'm going to say it's going to be width is 2. Right endpoint of that interval is 10.0 plus width is 3, right endpoint is 15.5, width is 2 from 5 to 7, right endpoint is 18.5, and width is 3, right endpoint is 20.0. Okay? That's my approximation. Is this greater than or less than the true value? Well, they told me that h is increasing. And we're using a right Riemann sum. So draw an increasing function, draw a right Riemann sum. You can tell it's an overestimate. This is greater than. I want to answer the question directly. I'm not going to say it's an overestimate when they ask me if it's greater than or less than. This is then the true value of the integral from 0 to 10 of h dt, because h is increasing. Okay, that's cool. Save that paper. The depth of the water in tank B, this is all the excitement in this question is here. So it's 3.2 plus, actually I don't need to graph this or anything. So I'm going to find the average value of G for 0 to 10. So 1/10 of the integral from 0 to 10 of this thing, 3.2 plus u, 17.5, square root of sine of, where do you even come up with these functions, you know? All right. The average value, which I'm going to let it think for a while. Okay, so 1/10 of the integral from 0 to 10 of g of t dt. So average for B, that's equal to 16.624. Average for A is 1/10 of the Riemann sum from part B, which is going to be, all right, this is going to be a little annoying. What? No, I don't even know where that is. All right, so, but I thought that the numbers were nice enough Oh, what I'm going to do is I'm going to divide through on one of these things. So I'll have like 2 times 1, 3 times 1.55. So 2 plus 3 times 1.55 plus 2 times 1.85 plus 3 times 2 is 6. And that's 16.35. Yes, okay, that's what I wanted to have happen. 16.35. But we knew this was an overestimate. So since average depth of A is less than 16.35, I know that average depth for A is less than average depth for B. Okay. According to the model given in part C, is the depth of the water in tank B increasing or decreasing at time t equals 6? Okay. The depth of B is G, so we need to find out the rate of change of B of G at t equals 6. G prime of 6 equals, oh, I wish I had typed that. I didn't realize I was going to need that again. I'm going to do math 8, derivative with respect to x of, copying the problem, 3.2 plus, I should have known not to type that in, because, right, it's going to take that derivative and it's going to be 0. Square root of sine of 0.16t at the place where t is equal to 6, and that's 0.887. So G, the depth of water in tank B is increasing. Okay, I would be a little more careful with my writing here, but I'm really trying to move quickly so that I can get out of here on time. It still might not happen, but I'm just saying for these, I'm moving a little quickly. All right, approximate G prime of 8 using the data in the table. And this one, I'm going to just say suppose they asked you to interpret this in the context of the problem, because this is the one that gets people tripped up. Okay, G prime of 8 is approximately equal to rise over run, so 2100 minus 900 divided by 10 minus 6. Games per week. They didn't ask for units of measure, but occasionally they will. And the interpretation is this represents the rate of change of G, right? But I'm going to copy their language for G, right? Rate at which games are being sold. Veterans of AP statistics will recognize this. It's just using a boilerplate sentence, right? Really takes a lot of the guesswork out of that. The rate at which games are sold, rate of change of rate at which games are sold, whatever. And games per week at time t equals 8 weeks. So, that's not a question they're asking, but if they did, that's how you would do that. Okay, approximate the value using a right Riemann sum for sub-intervals. Okay, width of the first is 3. Right endpoint is 450. Plus width of the second is also 3 to 6. Right endpoint is 900. Width of the third is 4. Right endpoint is 2100. And the width of the last one is 2, and the right endpoint is 2400. Okay, approximate the value, explain the meaning. G is the number of games per week, so if we add all that up, we're going to get the total number of games. Total games sold from t equals 0 to t equals 12 minutes, or weeks, minutes. Not selling that many games. Okay, here it is. One salesperson believes that starting with 2,400 games per week at time t equals 12, the rate at which games will be sold will increase at a constant rate of 100 games per week. Based on this model, how many total games will be sold in the 8 weeks between time t equals 12 and t equals 20? There's two ways you can do this situation. Either way, you have to cook up your own function. What I'm going to say is the new rate at which games will be sold, I'm going to call it n, right? Yeah, because they call the next one m. And except I'm going to let this take in a new variable like x. And x is not going to be t. N of x equals 2,400 plus 100x. So x is the number of weeks after 12. And n is per week. Meaning that if I want to find out how many are sold from 12 to 20, I can just integrate 0 to 8 n of x dx. Okay. Alternatively, if you wanted to have like n of t, where you were using the same t, you would have wanted to just make that t minus 12. But that's not, I know that's not always the first thing y'all would think to do. So I'm going to say, I think that y'all are going to be able to do this part on your own, right? Plug that into a calculator, run the integral, be happy. Another salesperson said, evidently somebody that took, I don't know, more math classes, the best model is a complicated exponential function. Based on this model, how many will be sold? Well, I'm going to integrate from 12 to 20 m of t dt. I'm going to run that through the calculator, and I'm going to get a total, and I'm going to round to the nearest whole number. And that's going to be the total number of games. That's all I've got for you. I hope this was helpful. If it was, hey, maybe you should like the video.